Okay, so this is going to walk you through how to convert between metric units as well as how to determine surface area to volume ratios for different shapes. So on the AP exam, you're allowed to use a formula sheet, and right here on the right you can see that the formula sheet provides you with metric prefixes, their symbols, and the factor that they represent. However, this may not help you if you're not great with math as far as doing metric conversions. So I'm going to show you a very elementary way to do metric conversions and sort of a foolproof method. So at the top of this I've written out the metric units. So here we have kilo, hecto, deca, base, which would be your base unit with no prefix, deci, centi, milli, micro, which looks like a U, but it's a Greek letter mu, nano, pico. So one way to remember this, kind of silly, but King Henry died, basically, drinking chocolate milk under 9 palms. And then you've got your metric prefixes in order, and all you have to do, since the metric unit is based on tens, is move your decimal place back and forth the number of jumps it takes to get from one prefix to another. Now, one other comment about this is it has to do with these jumps at the end, micro, nano, and pico, because milli is 10 to the negative 3, or 0.001 of a meter. But we jump to 10 to the negative 6th for micro, 10 to the negative 9th for nano, and 10 to the negative 12th for pico. That means that if you're going from milli to micro, it's going to actually be moving your decimal 3 spaces to the right, and micro back, same thing. So, for example, let's say that we were converting, let's say 0.033, and we're going to convert from, let's say, decimeters, and we're going to convert that to nanometers. So to figure out how many decimal places we're going to move, we can go up to the top. Here's deci, and we're going to be going to nano, so it's literally going to be 1, 2, 3, 4, 5, 6, 7, 8. We're moving the decimal 8 places to the right. So a couple things we can do here. First of all, if we're going 8 places to the right, we're basically moving it 10 to the 8th. So first way we can do this is we can take our 0.033 and we can literally draw in the jumps. 1, 2, 3, 4, 5, 6, 7, 8, add in zeros, and our answer is going to be 3300000, or 3,300,000. The other thing we can do is we can go ahead and change this into scientific notation before we make the move. In other words, 0.033 decimeters is actually 3.3 times 10 to the negative 2 decimeters. Now, we just said that we would be moving our decimal 10 to the 8th. So, all we have to do is add our exponents together, and we get 3.3 times 10 to the 6th nanometers. And if we come over here and look at our answer, same thing, 3.3 times 10 to the 6th nanometers. So if it's going to be something where you're going to end up with scientific notation, that's kind of a shortcut. Let's try another one. All right, so here's the second problem. So we have 7.1 times 10 to the 25th picometers, and we're going to hectometers. So we go to the top, all right, and we find pico right here, and we find hecto here. We're going to count our jumps. So it's going to be 3, 6, 9, 10, 11, 12, 13, 14. So we're going to be moving our decimal place 10 to the negative 14th, 14 spaces to the left. Now, again, it's going to take too much time if you're going to take 7.1 times 10 to the 25th, take it out of scientific notation, move your decimal around, and then put it back in scientific notation. So, easiest thing to do, we're moving our decimal 10 to the negative 14th, add our exponents together, and we get 7.1 times 10 to the 11th hectometers. And that's our answer. Alright, so another concept that we talked about in class has to do with the limitations on cell size. And basically what ends up happening is that volume increases by n to the third, and surface area, that's volume, surface area only increases by n squared. So what ends up happening is this ratio of surface area to volume gets smaller and smaller and smaller, and at some point, if we imagine that this is a cell, and this is a smaller cell, what's going to happen is, if after 1 hour, let's say that this is the distance that a particular solute can travel in or out of the cell in 1 hour, that would mean that in this cell, it would reach the middle. But in this cell, traveling the same distance in an hour, there would be this whole area in the middle where this cell would starve to death if this was some kind of nutrient it needed, or it would be poisoned if this was some kind of toxin that the cell needed to get rid of. So the way that a cell is most efficient is by being very small so that it has a maximum surface area compared to its volume. And if a cell is going to be large, like say a muscle cell or a nerve cell, we always find that those cells are very long and skinny, so that they have a certain amount of volume, but they've increased the amount of exposed surface or surface area so that things can get to the center quickly. Alright, and on the formula sheet, here are the formulas that you're given. We've got volume of a sphere, volume of a rectangular solid, volume of a right cylinder, surface area of a sphere, surface area of a cube, and surface area of a rectangular solid. They also provide you with the meanings of the different variables, side, surface area, volume, sum, etc. Alright, so I've given you here 3 shapes of different dimensions, and what we're going to do is walk through the formulas, calculate the surface area, the volume, the ratio of the surface area to the volume, and then we're going to rank them in order from the most efficient to the least efficient. Remember, the most efficient being the one that has the highest surface area to volume ratio. So let's start with the cube. So the surface area of a cube is 6 times the side squared. So that's going to be 6 times 0.6 squared. And working that out, we get 2.16 centimeters squared for our surface area. Now for our volume, the volume of a cube is basically length times width times height, or side to the third. And so that's going to be 0.6 to the third, and that's going to give us 0.216 centimeters to the third. So the ratio of surface area to volume for our cube is going to be 2.16 over 0.216, which gives us a ratio of 10 to 1. So there is our cube. Now, a nice thing that you can do with the surface area to volume ratio of a cube, turns out if you take the surface area formula and the volume formula, so we've got 6s squared over s to the third, we can reduce this, and the surface area to volume ratio should be 6 over s, or 6 over, in this case, 0.6. Here's our s, and we get 10 to 1. So we can double check ourselves and make sure that we did it correctly. If you don't get 10 to 1, you would know that you either got your volume wrong or your surface area wrong. Alright, next we're going to calculate the surface area of our sphere. So the surface area of a sphere up here is 4 pi r squared. So 4 pi, and our radius this time is 0.5 squared. And that works out to be 1 pi centimeter squared. You don't have to calculate it out with pi, because what's going to happen is you're going to end up canceling pi when you get your ratio. Now for our volume of a sphere, it's up here, 4/3 pi r to the third. So 4/3 pi, again 0.5 to the third. And for that we get 0.167 pi, and that's going to be centimeters to the third. Now we're going to calculate our surface area to volume ratio, which is going to basically be pi over 0.167 pi. Pi is going to cancel, and we get 5.988, or we can just round this to 6:1. So we have a 6:1 ratio. Now there's also a shortcut on this one to double check yourself. If you take your formula for surface area, 4 pi r squared, over your formula for volume, 4/3 pi r to the third, and reduce that, it turns out that 3 over r is a shortcut to get your surface area to volume ratio. So we can double check this. And 3 divided by 0.5 gives us 6. And so our 6:1 ratio works. So now we've got a 10:1 and a 6:1. And now finally we're going to do our rectangle. So for the rectangle, they give us a surface area formula that it is the sum of the surface areas of each side. I don't care for the way they write that. I think probably a better way to write that is that it's going to be 2 times the length times the width plus the length times the height plus the width times the height, which is basically their formula, but I think it's a better way to write it out. In other words, 2 sides of this rectangle are going to be length times the width, and then 2 sides of the rectangle are going to have this length times height, and then the final 2 sides are going to be the width times the height. So since there's 2 sides that have each of these things, we multiply it by 2. But I like it spelled out this way better. So for our rectangle, it's going to be 0.7 times 0.3 plus 0.7 times 1 plus 0.3 times 1, and then we'll multiply the entire thing by 2. And when we do that, we get 1.21 centimeters squared. And now for the volume of a rectangle, that's easy. It's just length times width times height. So it's going to be 0.7 times 0.3 times 1, which is going to be 0.21 centimeters to the third. So our ratio is going to be 1.21 over 0.21, and that gives us a ratio of 5.76 to 1. So the only thing left to do now is to put these in order by rank from our most efficient to our least efficient. So our most efficient in this case is our cube, 10:1, followed by our sphere with a 6:1, and finally our rectangle with a 5.76 to 1. And that's how you work out problems with calculating surface area to volume ratios.